So along that vein, I'm going to present you some stuff which is not in the text, but I think is stuff that you should know about. Okay. So in particular, I'm going to start off with the Laurent expansion, okay, which Stein leaves to one problem. He leaves it to one problem in the problem section. But I think this is important enough that we should talk. So today I'm going to present sort of like stuff that I think would be helpful to you and is for some reason left out of the text. Okay, so so we're going to start off with this thing called the Laurent expansion. And yes, this is the Laurent expansion, the word that I apparently say so strangely. Yeah. let me not walk down that path. Let me not start telling that story. Okay. Okay. So it's basically it's sort of like a power series expansion, but when you have a singularity, or you have singularities. So the setting is this. You have an annulus. Okay, so an annulus, that is to say a ring. In case you don't know what annulus means. So something like this. And your function is holomorphic on the annulus. So it's holomorphic outside of this inner disk, but inside this outer disk, and it has some singularities. It may have some singularities inside here. Okay, so it turns out that it's possible to get something like a power series expansion for this function. Okay, and that's called the Laurent expansion. Okay, so so here's the setting, right? So you have this annulus A. It's centered on some disk centered on some point Z0. There's an inner radius little r, there's an outer radius big R. Okay, so you have F holomorphic on the annulus, which is all the points whose distance from Z0 is between little and big R's. Okay. Then for any point in the annulus, you can actually write. There's this expression, sort of like there's the sum from 0 to infinity. So there's a term that looks basically like a power series. Okay, and then there's another term which has the negative powers from n equals 1 to infinity. Okay, so you have this power series. Sometimes people abbreviate this as summation from negative infinity to positive infinity, a sub n, c minus c naught to the n. But really, it's the sum. By that, they mean the sum of these two series. Okay, where the coefficients can be obtained as by taking the integral of f of zeta over zeta minus z naught to the n plus 1 d zeta over c rho z naught, where c rho z naught is any circle centered at z naught. So a radius rho around z naught, where rho is between little r and big R. So you can take any circle rho, circle radius rho inside the annulus. you integrate this thing, and that gives you the coefficients. Okay. And so this is the Laurent series. Okay. So right. So this right. It's called the Laurent series of F around Z0 in the annulus. Right? Okay, and then yeah, the Laurent series of your function, in this annulus. Okay, so the proof of this is pretty straightforward. You say, well, look, so here's Z0, here's A, and let's take some point Z inside the annulus. So fix some point Z in the annulus. Okay, and let rho denote the distance to the center. Okay, so this distance is rho. So rho is between little r and big R. Okay, and we're going to choose two other disks that are still in the annulus, but so they're right. We choose two disks that are contained inside of the annulus. Okay, so we're going to call those things rho. The big guy is going to be rho 1, have radius rho 1, and the little guy is going to have radius rho 2. Okay. So choose these other radii, rho 1 and rho 2, such that they bracket the point. Okay. Okay. So we have these two guys. Here's the point of interest, right? And so what we're going to do is just use the Cauchy Integral Formula on the function, right? So if you orient these guys positively, right, then you get that the f of z is going to be the integral. Wrong way. The f of z is going to be the integral of the outside guy minus the integral of the inside guy, right? That's good, right? Because it's gonna be holomorphic, right? You create something like this, right? You create this sort of keyhole region like this, and you can use Cauchy Integral Formula on that, right? Yes, good. Right, so you get the integral over the big guy. Let's call that guy C1. So the outside guy is going to be C1. The inside guy is going to be C2. So the integral over C1 of f zeta minus C minus the integral, the same thing over C2. Right. I hope everybody's happy with this.
These are circles of radii.
These are the ones that we just picked out here. So this is C1 and this is C2. And the point is that they're contained inside the annuli. Annulus, excuse me. Okay, so now we the two parts of the Laurent series come from these two expressions. Okay, right. So on C1, we're going to play the same trick that we used to get the power series. So say, well, look, so let's call these guys 1 and 2. Okay, so in 1, we express, so this is the trick that we played before, right? We take 1 over zeta minus z. We say, well, that's the same thing as we work in the. We want to express this thing as a power series around z naught, and so we work in the z naught, right? We say, well, look, zeta minus z is zeta minus z naught minus z plus z naught, right? We subtract a z naught and we add a z naught. Okay. And so, right, so we get this zeta minus z naught minus z minus z naught. Right? So we do that, and then if you recall, we factor out we factor out the zeta minus z naught, and we're left this 1 minus z minus z naught over zeta minus z naught. Right? And then from there, what do? Anybody remember what we did when we were making the power series? Yeah, go ahead.
A geometric series.
We have geometric series, right? So this z minus z naught, right? Z minus z naught is smaller in magnitude than zeta minus z naught, right? Because we're on C1, right? So we get this, right? This is smaller than 1, right? And so we use the power series expansion for 1 over 1 minus z. In other words, the geometric series. Right, so we get summation z minus z naught over zeta minus z naught to the n as n goes from 0 to infinity. Right? Okay. Then on 2, we can't use the same expression, right? Because z minus zeta minus z naught is smaller than z minus z naught in that case, right? Because we're on the inner disk, so zeta minus z naught is going to be smaller than z minus z naught. Okay, so we play the trick. We say, well, let's write zeta minus z as here's the clever thing, negative z minus zeta. Okay, right, so we throw in this negative, and that allows us to write it like this, z minus z naught minus zeta minus z naught. Okay, right, and now we play exactly the same trick as before. We factor out the z minus z naught. Now we're dividing by z minus z naught, and so we can still use the geometric series. Yeah, so in my notes I have amazing trick. Okay. Yeah. So what do we get? 1 over zeta minus z is going to be negative 1 over z minus z naught, 1 over 1 minus zeta minus z naught over z minus z naught, right? Which turns into negative 1 over z minus z naught, summation zeta minus z naught over z minus z naught to the n from n equals 0 to infinity. Okay. In other words, negative summation zeta minus z naught to the n over z minus z naught to the n plus 1. Okay, and the point is that that so notice that each sum converges uniformly, right? Because we're inside the disk, right? We're strictly inside the radius of convergence. Okay, this is the trick that we used last time when we were talking about power series. Okay, so what's good about that? So remember what we had. So we had that F was this guy, right? Minus right? We have this, and now we have these expressions to use, right? So we get 1 over 2 pi I f zeta, then we get this z minus z naught to the n over zeta minus z naught to the n plus 1 d zeta, right? And we get something similar for the other guy. 1 over 2 pi I integral over C2 f of zeta thank you. Right, so we get a plus now because it was negative, so we get zeta minus z naught to the n over z minus z naught to the n plus 1 d zeta. Okay. Right, but the point is that, whoops, there should be summations. What am I doing? The point is that because of uniform convergence, we can pull the summations out. Right, we can pull the summations out, and so we get summation 0 to infinity, and also 0 to infinity. Right, yeah. Okay. Okay. But this is what we wanted, right? So here, look, right? We can do the integrals term by term, right? This is independent of zeta, so we can pull that out. That gives us the power series portion. Right. F zeta over zeta minus z naught to the n plus 1 d zeta. Z minus z naught to the n, right? And then the other piece gives us the negative part, right? Right, plus 1 over 2 pi I f zeta minus z naught to the n d zeta 1 over zeta minus z naught to the n plus 1. Okay. And I'm going to shift the index up by 1. So I'm going to make n go from 1 to infinity. So this becomes an n minus 1, and this becomes an n. Just to make it look more like what I had written. Okay. Okay. Yeah. Yeah, if you don't mind, I'm gonna move this to the bottom so that it becomes, so this thing becomes zeta minus z naught to the negative n plus 1. It doesn't. It's the same thing, of course. But that allows it to look more like more symmetric. Okay, everybody good? So this is it, right? This is the Laurent. This is right. This is our a sub n, and this is our a sub negative n, right? As desired. Okay, so, okay, and it's easy, if you think about it a little bit, this expression converges uniformly on any closed subannulus. So just a remark. The Laurent series converges uniformly on any closed subannulus. Okay, just for the same reason that, because it's a it's a combination of power series, right? You've got one power series, right? You've got the first power series which converges on this disk, so it converges uniformly on any closed disk inside there, right? The other one is a power series in 1 over z minus z naught, so it converges outside of a disk and uniformly on any outside of the closed disk, right? And so the two of them will converge on the intersection, converge uniformly on the intersection. Yeah, fine.
In the statement of the Laurent expansion, we say the coefficients are equal to like 1 over 2 pi I times the integral. What is that integral over?
The integral is over any curve, any simple closed curve inside the annulus.
Okay.
So just you take any curve that you just think you can take any circle inside the annulus.
Okay. Because I thought in our derivation, like we needed, C1 to have smaller radius and C2 to have bigger radius.
Oh yeah, that's true. But think of what these things are, right? These things are, you can deform them, right?
Yeah.
You can deform them to just one common to one guy there.
But that passes through. Okay.
Sorry, there's some. Sorry, I've written something wrong here. No? No, that's right. Yeah, right. It doesn't matter because this thing, right, is holomorphic. This thing is holomorphic within the annulus, right? So you can deform it. Doesn't matter.
Okay.
Right. It's not dependent on z. Right. This doesn't have z on the inside. It has z not on the inside.
Yes, I see. So sorry to clarify. Our choice of C1 and C2 was necessary so like we could create the contour, we can get all the geometric series to work, but then in the end we pull out the things that require C1 and C2. So now
so
we can
at the end,
C1 and C2 into the same curve, which is any curve in the annulus.
Yes. Okay. Thank you, Kyle. I didn't say that at all, and that's good.
No, okay. I wasn't sure exactly what.
No.
Okay.
No.
Thank you.
Yeah. So I should say then at the end you deform to some. You can take these C1 and C2 to be the same curve. To be any curve inside the annulus. Okay. 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 Everybody okay? Yes. Okay, just an observation. So, remark. Notice that the coefficients are unique in the Laurent expansion because for if you take any gamma, so like a circle centered at Z0 inside the annulus, then what happens when you integrate? What happens when you integrate over? What happens when you integrate over that circle? What do you get? So, for example, what happens when you integrate this guy? So, hey, you've got the Laurent expansion. What happens when you integrate this?
You pick up the residue.
You just pick up the residue, right? Everything else vanishes, right? Uniform convergence means you can pull this out. You integrate one by one. Everybody has a antiderivative, right? So they all vanish except for the 1 over z minus z naught. So that picks up the residue, right? And so that tells you that the residue is no matter what if you have two supposedly different Laurent expansions, well, the residues are going to be the same, right? That coefficient has to be the same, and it's of course true for the other coefficients, right? If you take f of z times z minus z naught k plus 1 dz. I'm sorry, you should get 2 pi. There should be a 2 pi I here, but anyway. Okay, so if you do this, right, then you're taking the Laurent expansion and then you're hitting it with this, right? Well, that's just going to pick off the residue of the shifted guy, right? And so that will give you the kth coefficient, right? So so the coefficients can't be different, right? The coefficient, right? The coefficients can't be different. So, yeah. Okay, so this actually has sort of a funny application, a sort of contrived application. So here, for example, let's see how I should do this. Okay, so here's the contrived example to show that that this integral, so for any simple closed curve around the origin, to show that okay, so here it is. Okay, so this could be a problem in the homework, right? Like, show that for any simple closed curve C around the origin that this equality, that this formula holds true. 1 over 2 pi I, the integral over e to the 1 over z to the negative n plus 1 dz is 1 over n factorial, right? So it looks kind of, maybe looks kind of daunting, but then you realize that, what is this thing here, right? This is the coefficient from the Laurent expansion, right? So you realize that this thing here is a sub negative n, right, from the Laurent expansion of e to the 1 over z. Right. That's how we get the coefficients from the Laurent expansion. Right? Integrate the function against z to the index plus 1. Z over z, yeah. Okay. So you say, okay, well, this is actually the negative nth coefficient from the Laurent expansion, and so all you need to do is find the Laurent expansion for e to the so what's the Laurent expansion for e to the 1 over z? Well, the power series expansion for e to the z is, of course, z to the n over n factorial, right? Right, and so right, and that's valid. That's valid for all z, right? So that's valid for all z. Right. So if you look at e to the 1 over z, as long as z is not equal to 0, then we can use the power series expansion. We can use the power series expansion on this, right? So you get 1 over z to the n, n factorial. Right? So you get 1 over n factorial, 1 over z to the n. Right. So as long as z is not 0. Right. And so you found an expansion for e to the 1 over z. We know that this must be the Laurent expansion because the Laurent expansion is unique, right? And so what's the negative nth coefficient in the Laurent expansion? It's 1 over n factorial, right? And so that's all this is saying, that the negative nth coefficient from the Laurent expansion of 1 over e to the 1 over z is 1 over n factorial. So that's it. Okay, so you've just proven some sort of, I don't know if this formula is ever useful to anybody, but in any case, you could get it this way. Yeah, don't be impressed by that. Yeah, I have other examples, but I'm not going to show them. Okay.
So
yes.
In general, you could use this replace e of 1 over z.
Yes. Yes, exactly. So just put in some other function here. As long as you, by whatever method you feel like, right, by hook or by crook, you come up with some. You come up with the Laurent expansion, by your own, trickery. Then you get this. You get some formula. You get some series, an infinite series of formulas. Okay. So yeah. Okay. So in particular, if one has an isolated singularity at some point, so you're right. So there's, you're analytic on some punctured disk, but you have a singularity at the center of the disk. Then you have a Laurent expansion. Right, you can get a Laurent expansion on that punctured disk. Okay. So, like I was saying earlier, Stein defines things in ways that are a little bit idiosyncratic, I'd say. Let me. You can define. Remember, we had singularities, removable singularity, poles, and essential singularities. That's, I think, a bit easier, more easily expressed in terms of the Laurent expansion. So, what's a removable singularity? It means that that when you take the Laurent expansion in the disk, then it's just a power series expansion, right? It has no negative terms, right? What does a pole mean? A pole means that you have a finite number of negative terms. What's an essential singularity? It means that there are an infinite number of negative terms. Okay, and so I think that's probably an easier way to think about singularities than the way that Stein presents it. Okay, so right, so you have Laurent. I'm just going to write it up. What I just said. You have a Laurent expansion. And from negative infinity to positive infinity. If a sub n is 0 for all n less than 0, we call Z naught a removable singularity. If a sub n if a sub negative k is non-zero and a sub n equals 0 for everything less than that, we call Z naught a pole of order k. And if a sub n is non-zero for infinitely many negative terms, we call a sub n an essential singularity. Okay, and those definitions are equivalent to Stein's, right? Like, if all these terms, if all the negative terms, if all the negative coefficients are 0, well, you've got a power series expansion, right? You've got a power series that converges, and it also converges at the center, right? It also converges at the center. So, so you've got you've got a function that can be extended to a holomorphic function in the disk, which is Stein's definition, right? And conversely, right, if you have such a function, then definitely you're going to have the Laurent series where all the negative terms are 0, negative coefficients are 0, right, et cetera, et cetera. Everything translates over. But I think this is a bit more succinct, easier to remember. Yeah, so I was setting this up on the exam, actually. So one of the exam problems that I gave was, I think, the following. So you have, so one of the problems was like this. if you have f is holomorphic on some punctured disk, BR Z naught. Okay, and the limit of as z goes to z naught, oops, of z minus z naught times f of z is 0. What?
Wait, no, nothing.
Okay. Then 1 over 2 pi I, the integral of f of z, z minus z naught to k minus 1 dz equals 0 for k equals 1, 2, 3. Okay, for yeah. So for C circle, some circle inside where R is less than big R. Right? So you have Z naught here, right? And you take some circle here, C sub R, and I want you to prove that the integral of that thing over C sub R is 0. Okay. Now, what's the point? The point is that you're allowed to deform this. You can shrink it as much as you want, right? Because it's holomorphic in a punctured disk, right? So you can play as usual, you can play the keyhole region game, right? So you're allowed to shrink this as much as you want. So, right? So, would anybody want to say how they got this, or if they got this? Anybody get this? Jade, go ahead.
If the limit as this is 0, then you can't have any more terms that are non-zero, because otherwise the thing will blow up.
So you're using the Laurent expansion, basically? You're saying use the Laurent expansion and then, yeah. Yeah, so, yeah, but pre-Laurent expansion, did anybody? So that certainly works. Once, no, yeah.
What I said, I feel like maybe this is a bit clunkier than it needs to be, but what I said is like...
Clunky is okay.
Either it's a removable singularity, in which case we just fill it in and we have a holomorphic function, so the integral is 0.
Yeah.
Or it's a pole, in which case the fact that that limit is 0 shows that the residue at z naught is 0, in which case by the residue formula, the integral is 0.
I guess so either it's removable or it's...
And we know it can't be essential, because then f of z would be dense near z naught, so the limit wouldn't be defined.
Okay, yeah, that works, right. Yeah, because you couldn't have a principal part, you couldn't have anything lower than -1, the power -1. That works. Anybody? So I'll show you even clunkier. Okay, so this is even clunkier than that. You say, well, I'm going to take a circle of radius r. So take a circle of radius r smaller than 1, where r is chosen so that but you know that this thing, whoops. You know that this thing goes to 0, right? So you know that you can make this thing smaller than epsilon over z minus z naught. So for some fixed epsilon. So fixed epsilon. Right. Fixed epsilon, you know that you can choose since the limit goes to 0, you can find some tiny circle in which on which this thing is controlled by this, right? Right. Okay. And then you just use the ML theorem, the triangle inequality. You say, well, then 1 over 2 pi. Then the integral. Well, let's see. So the integral over that radius is of course controlled by 2 pi times the radius over 2 pi, right? And then we have this f, which is just epsilon over z minus z naught is r, right? And then we get an r to the k minus 1. R to the k minus 1. Right? So I'm just bounding this term, right? This part in absolute value is controlled by epsilon over r. This part is equal to r to the k minus 1, right? And then we get the length of the curve, which is 2 pi r, right? So you get this, right? And this is smaller than epsilon because r is smaller than 1, right? And k is bigger than, k minus 1 is bigger than 0, right? So what does that give you? That gives you that we can make this integral smaller than any epsilon, and so it must be 0. Right, the size of the integral is less than any epsilon. Okay. Questions? Yeah, Kai.
What about the case where k equals 1?
When k equals 1, it's okay because you still get epsilon, right? Then you get r to the this. You just get epsilon there, so it's all right.
Or, yeah. Okay.
Okay, so, right. Okay, so what's the point? Right, if f is holomorphic in some punctured disk and this equals 0, then all of the negative coefficients are 0 in the Laurent expansion, right? So this is another way of characterizing removable singularities, right? Although maybe it's easier to do. We could have done maybe more cleanly. Okay. So, yeah, okay. So this is another way of characterizing removable singularities. Yes, Nish.
So similarly, on the exam, I just said this means it's a removable singularity. Then the residue is 0. That's why we have 0 in the end. Is that okay?
Let me take a look at it because it sounds a bit more sketchy than Noah's argument. So let me take a look at it.
That's right.
Let me take a look at it. It's like being a lawyer or something. I have to see exactly what you wrote. Okay. So yeah, so that's all I want to say about that stuff for now. Okay, so I'm gonna hop, sort of change gears and do something else right now. Oh yeah, so actually no, I'm not gonna change gears. Sorry, let me state a theorem here. So there's sort of a useful extension of Cauchy-Goursat that comes out of this, which is that if f is homomorphic on a disk D, excluding a bunch of points zeta 1 through zeta k, say. for all j, this limit is 0. So if, as z approaches zeta j, then for any closed curve in the disk. Okay, so this is just saying that all this is saying is basically that you can fill in those singularities, right? Because what this condition means is that each of those singularities was a removable singularity, and so you can still apply Cauchy's theorem. Okay, so that's basically all this is saying. But this will come in handy. Okay, everybody okay? So, I slept for only 4 hours last night because I was thinking so much about this class. This class worries me. It's on my mind like 100% of the time. No, like 90% of the time.
I'm sorry.
Yeah. Well, it's okay. It's my own fault for choosing this book. I trusted Stein. I actually had a class with Stein many years ago. Yeah, there was like a week. We had this thing at University of Wisconsin-Madison. Each week was taught by a different, famous harmonic analyst. Anyway, Stein was the last one, and he was at the time getting more and more into like number theory. So, yeah. Okay. Yeah, mainly what I remember was that he would whip around and say, "What?" Whenever anybody had a question. That's all I remember of Stein. Okay. Okay. So now I'm going to change gears, sort of, and talk about something that Stein leaves out as the notion of winding number. Which is pretty simple, but allows you to have some geometric interpretations of things that don't look so obviously geometric. So basically, I'm introducing this so that I can rephrase Rouché's theorem in a geometric way. Okay, so that's what we're heading towards. Okay, so heading towards. So like geometric interpretation. Okay, so so this is it. So let's recall that for C, a circle around some point, we know that if you integrate 1 over z minus z naught dz, then you get 2 pi I. That's something that we use all the time. Integrate a circle, right? You get 2 pi I. Right? Okay, so here's the lemma. Yeah, let's do it. Okay, so here's the lemma. So let So this lemma is just going to say that basically, whenever you have a point and you have a sufficiently smooth curve that that goes around, or maybe doesn't go around Z0, then when you integrate, whenever you integrate this over such a curve, you're going to get something of the form, 2 pi I times some integer. Okay. So we have our point. Let gamma from alpha gamma. Let gamma be a piecewise continuously differentiable curve that doesn't pass through Z0. Then that integral is a multiple of 2 pi I. Okay, so the proof of this is not the most exciting. Let me show you how. Let me give it to you anyway. So let h of t. So define a function h of t being the integral from alpha to t of gamma prime s over gamma s minus z0 ds. Okay, so this is just obtained from this integral, right? So you take this integral, but you integrate from up until a fixed time. Okay. So h is continuous on AB, on alpha beta, and is differentiable where gamma prime is continuous. So gamma prime is continuous, remember, except at a finite number of points. So there's just a finite number of points where this h is not differentiable. Okay. With derivative, of course, being gamma prime t over gamma prime minus c. Okay, so I'm just going to sketch it out rather than make you more sleepy. One, observe that e to the negative ht gamma t minus z0, the derivative of that is 0. So that's just a calculation. You do the product rule on it. That's easy. So and so is constant. So that tells you that e to the negative ht gamma t minus z0. So this thing is going to equal to its value at time alpha, right? So e to the negative h alpha gamma alpha minus z0, right? But H alpha is 0, right? So this becomes 1. Right. And so what does that tell you? That tells you that e to the ht must be gamma alpha minus, gamma t minus c naught, or gamma alpha minus c naught. Okay. Right. Remember what we're trying to show. So our goal is actually, we want to show that h at beta is a multiple of 2 pi I, right? Is a multiple of 2 pi I, right? Because that's h at beta is this integral, right? We want to show this is a multiple of 2 pi I. Right. Well, putting in beta here, at t equals beta, we get gamma beta minus c naught over gamma alpha minus c naught equals e to the h beta. Right. But alpha and beta, I'm sorry, gamma alpha and gamma beta are the same because this was a closed, right? Sorry, this, I should have said, this should be a closed curve. Sorry. Okay, so gamma alpha and gamma beta are the same, so this is 1. So e to the h beta is 1, and that tells you that h beta must be a multiple of 2 pi I. Right. E to the h beta is 1. That tells you that h beta must be a multiple of 2 pi I. Okay.
Why do we have the derivative time of the, like, e to the minus ht times gamma t minus z0? Why is that thing 0? Is that just by computation, or is that?
Yeah, it's just a computation.
Okay.
You do the product rule.
Okay.
Yeah. Just by just use this fact. Yeah, I don't want to do the product rule.
That's okay.
Okay, so in any case, the point is that, if we look at this thing divided by 2 pi I, we get some integer. Okay, and that integer basically tells you how many times you go around the point. So if you go around the point, clockwise, you get positive integers. If you go around the point, counterclockwise, you get negative integers. Okay. And so this gives the concept of a winding number. So here, so the winding number of gamma with respect to z naught is defined as I'm going to notate it as n of gamma comma z naught. It's just, as you might expect, the integral of dz over z minus z naught over the curve gamma. Okay, and this is also called the index of the point z naught with respect to the curve gamma. So, depending on if you are point centric or curve centric. Okay, so this gives us, we can combine this with the Cauchy integral formula in the following way. Cauchy integral formula with winding number. Okay, so F holomorphic on some open disk D, and gamma a closed curve in D. If Z naught is in D and not on gamma, then f of Z naught, then the integral over the curve of f of Z, Z minus Z naught dz is the value of the point, but times the winding number. Okay, and this is what you might expect. And you could prove this some other way, but I'm going to prove it one way like that. At this point, you can. I think it's pretty simple to figure it out. But let me show you how one way to prove it. That's kind of cute. We have time for it. Okay. Okay. So let capital F denote the difference quotient, f of Z minus f of Z naught over Z minus Z naught. Okay, now observe f is analytic for Z not equal to Z naught, of course. Right? Further, the limit as Z goes to Z naught of Z minus Z naught times F, well, that's 0. Right? Because you're going to get Z minus Z naught times F is just the difference. And as Z goes to Z naught, that goes to 0. Okay. So what does that tell you? Right? So we've got this function, it has a singularity, but it's a removable singularity. Right? It's a removable singularity, and so when we integrate f over gamma, we get 0. Right? That is, we get 0 equals the integral of the difference quotient over the curve. Right? But what does that tell you? That tells you that the integral of f of Z over Z minus Z naught dz equals the integral of f of Z naught over Z minus Z naught dz over that curve. Right? That is to say that you get that this thing, right? This thing equals this thing times 2 pi I times the winding number times the winding number of gamma over Z naught. Okay, that's it. Bye. Okay, so yeah, I'll probably continue with some more sort of extra material next time, because there's some cool stuff that is left out of this book that I think is fun for you to know. Oh yeah, so we haven't gone to Rouché's theorem either. So next time, geometric interpretation of Rouché's theorem.